Have you ever wondered how your computer can run dozens of programs at the same time, even with a single processor core? You've got a browser open with 20 tabs, a music player streaming your favorite playlist, a word processor, and maybe even a game running in the background. It feels like magic, right? Well, today we're going to demystify this magic and dive deep into the world of CPU scheduling. It's the secret sauce that creates the illusion of multitasking. And I promise by the end of this video, you'll see your computer in a whole new light. So let's start with a simple analogy. Imagine your computer's single-core CPU is a one-lane highway. It's just a single road, no passing, no extra lanes. Now, imagine all the programs and tasks you're running are a massive convoy of trucks. You've got hundreds, maybe thousands of them, all lined up, and they all need to get to their destination using this single-lane road. How can they all move forward at what seems like the same time? If one truck just drove straight to the end, all the others would be stuck waiting in a massive traffic jam. Your music would stop, your game would freeze, and your browser would become unresponsive. That sounds like a terrible user experience, doesn't it? Our computers are much smarter than that. This is where the concept of time slicing comes into play. The CPU, or our road manager in this analogy, is incredibly fair, but also incredibly strict. It tells the first truck in line, all right, you can drive, but only for a very, very short distance. Let's say 1 meter. After that truck moves its 1 meter, it has to pull over immediately. Then, the CPU tells the second truck, your turn. You also get to drive for 1 meter, then the third, the fourth, and so on, all the way down the line of hundreds of trucks. Each one gets a tiny equal slice of time on the road before it has to yield to the next one in line. From a bird's eye view, what would this look like? You'd see the entire convoy of trucks inching forward together. No single truck makes a lot of progress at once, but the whole group is advancing. This is exactly what your CPU does, but on an unimaginable timescale. It switches between tasks, your browser, your music, your operating system millions of times per second. Each task gets a few milliseconds of processing time before the CPU kicks it out and brings in the next one. This rapid rotation happens so fast that, to our human perception, it seems like everything is running smoothly and simultaneously. It's a beautifully orchestrated illusion. But wait, there's a cost to all this switching. Let's go back to our trucks. Every time a truck has to pull over, the driver can't just jump out. They have to do a few things first. They need to record exactly where they stopped, check their fuel level, note their current speed, and basically save all the important information about their current state. Then, when it's their turn to get back on the road, they have to spend time reviewing that information to pick up exactly where they left off. This process of saving and loading information takes time and effort. It's not part of the actual driving. It's overhead. In the world of computers, this overhead is called a context switch. When the CPU decides to switch from running your browser to running your music player, it first has to save the complete state of the browser task. This includes all the data in its registers, the program counter which points to the next instruction to be executed, and other management information. It's like taking a detailed snapshot. Then it has to load the snapshot of the music player task that was saved the last time it ran. Only after all this loading is complete can the CPU actually start executing the music player's code. This saving and loading process, this context switch, consumes valuable CPU cycles. The processor is busy doing administrative work instead of actual work, like rendering a web page or decoding a music file. So, while time slicing is a brilliant solution, it's not free. If the time slices are too short, the CPU will spend most of its time just context switching, like our truck drivers spending more time on paperwork than on driving. The overall system performance would grind to a halt. If the time slices are too long, the system starts to feel sluggish. You might move your mouse, and it takes a moment to respond because the CPU is busy with a long task and hasn't gotten around to processing your mouse input yet. Finding the perfect balance is the art and science of operating system design. It's a constant trade-off between responsiveness and efficiency. Let's really hammer home this idea of illusion. Imagine a classic flipbook. Each page has a drawing that's slightly different from the one before it. When you flip the pages quickly, your brain perceives continuous motion. You don't see individual static images. You see a moving cartoon. CPU multitasking is the digital equivalent of that flipbook. Each page is a tiny slice of work done on a specific task. The CPU flips through these tasks at such a blinding speed that your brain can't distinguish the individual slices. It merges them into a seamless experience of parallel activity. You hear your music without interruption, you see your video play smoothly, and you can type in your document, all because the CPU is a master illusionist, juggling these tasks faster than the eye can see. So for decades, engineers made CPUs faster and faster. This meant our single-lane road had a much higher speed limit. Our trucks could cover their 1 meter of distance in a fraction of the time, and the context switching also got quicker. This made the illusion of multitasking even more convincing. We could run more complex programs and have a smoother experience. But eventually we started hitting physical limits. Making that single lane infinitely fast just wasn't possible due to constraints like heat and power consumption. The traffic was getting heavier, and simply increasing the speed limit wasn't enough to handle it. So the engineers thought, what if we can't make the road faster? What if we add more roads? This is where multi-core processors come in. Instead of one super-fast lane, a dual-core CPU is like having a 2-lane highway. A quad-core CPU is a 4-lane highway, and so on. Now you can have multiple trucks driving at the exact same time, each in its own lane. This isn't an illusion anymore. It's true parallelism. Your computer can assign your game to one core, your web browser to another, and your operating system's background tasks to a third. They are all genuinely running simultaneously, with no need for rapid time slicing between them. Of course, the world isn't that simple. You often have far more tasks than you have cores. If you have a quad-core CPU but are running 50 tasks, you still need the magic of CPU scheduling. But now, you have 4 schedulers, one for each lane of the highway. Each core juggles its own set of tasks using time slicing. So you get the best of both worlds, true parallelism across the cores, and the illusion of parallelism for the tasks running on each individual core. This human C tactics approach, throwing more workers at the problem, has been the driving force behind the performance gains we've seen in the last decade and a half. In conclusion, the smooth multitasking experience you take for granted on your computer is a masterclass in clever engineering. It's a combination of the time-slicing illusion on single cores, which juggles tasks at incredible speeds, and the true parallelism offered by multi-core processors, which allows tasks to run side by side. The next time you're effortlessly switching between a dozen applications, take a moment to appreciate the silent, frantic, and beautifully complex dance happening inside your CPU. It's the unsung hero that makes our digital lives possible. Thank you so much for joining me on this deep dive into CPU scheduling. If you found this explanation helpful and want to learn more about how computers work their magic, please hit that like button and subscribe to the channel. Let me know in the comments what other computer science topics you'd like me to bring up. Thanks for watching, and I'll see you in the next video.